All right, so one thing I wanted to point out really quickly. So I saw this today and I thought it was just kind of interesting to point out some of the security issues we have. So making a little public push for a class I teach in the spring, that cybersecurity and some of the things that we talk about in there. So this was interesting that a hacking group put up over 3 terabytes of private videos from home security cameras. There's some issues with them, the way they're done. We've thought there were some backdoors in some of them. There's a reason that the federal government has banned on any federal installation some of these brands. Part of it is people just don't change passwords. So it's interesting, but what's more interesting is they put it up for sale, and they actually have had at least 70 people that have paid $150 to get that. Interesting. There's money. That's part of the issue with cybersecurity is it's being monetized. People want to make money out of it. There's a lot of other reasons that people do things, but the monetary aspect is certainly one of them. And we see that in ransomware and some other things. So this base knowledge you get in a course like this then can translate into that cybersecurity world where you have a little more information, a little more knowledge about why things happen. And it comes at an appropriate point because of what we're going to talk about today. In some ways, we break apart our networks to make them a little more secure. So, if you haven't enrolled for the spring and summer, because that's both out now, you should probably start looking at that option. And I know everybody this year, it seems like we're all behind, both faculty, students, and everybody. So get enrolled as soon as you can. Get your advisor on the horn and go, hey, I need to figure out what I need to enroll in. If you don't have a 4-year plan, if you already have a 4-year plan, you still need to go through that advisor. We put locks on every semester so that you can't, hang on, lost my Deseri, so that you can't enroll without contacting that advisor. And it's really just a check so that you have to work through there. Well, maybe I won't use, interesting. All right. I was connected a second ago. Always interesting when you have a network issue, and I'll explain a little bit of that. So what we're going to talk about today and this week is how do we break apart these networks. So we said, all right, we're going to physically connect them, but there's some reasons we need to do some limits, and we'll talk about what those are, and how do we break them into workable segments and what it's talking about. So we try to do something called segmenting a network. So we break it into pieces, and one of the biggest reasons is each piece then is its own broadcast domain. So you've already seen from when we ran Wireshark that these networks are pretty chatty. Everything's communicating back and forth saying, who are you, what's your address, and anything in that domain, that broadcast domain, everybody gets to see it. Well, if you start getting 10,000 computers on there, it's kind of ugly for all that traffic. So our performance will go down. If there's an issue, and I just have one big giant flat network, well, my troubleshooting's a lot tougher. And one of the biggest ones we're starting to push is how do I design my network for security from the ground up? Or how do I go back and implement some security pieces on my network? We know that security is kind of where we're headed to. So typically we break up our network into a couple of different ways. So on an organization such like as Peru, where we might break it up by building, by floor, so geographic locations, departmental borders, so maybe we have different organizations in a company, so School of Ed would get a different piece of the network than the School of Professional Studies might. And so we make those decisions, we hopefully do that, and so we can then broadcast out. So if we need to, we have ways we can broadcast to the entire network, but notice we're breaking it into a couple of smaller networks. Easier to manage, higher performance, less overhead then. And if something goes wrong, it gives us some additional troubleshooting steps. If I know that both domains, in this case, are down, then I can go, oh, well, then something's happened above that level, however we're separating those. And so we can separate them on a physical layer, and sometimes we do that for the maximum security. But we can also do something called VLANs we'll talk about here. So, companies growing. We went from 20 or 30 computers to having a couple hundred. And that very much mirrors what's happened at Peru. I've worked with several organizations that have went that size, and suddenly they've grown. And they had one router. Everything in that entire company goes through that single router. We needed a way to start to break up that traffic. We needed a way we could start to isolate different areas. So we have to figure out how we're going to divide it geographically, logically. Does it make sense? So if we're a multi-story building, each floor might make sense to do that geographically, depending on that organizational structure. So sometimes that geographical model works. And so this might be the option that we picked. And so we broke it into each floor has its own switch, and that's pretty common in terms of distance limitations. And so what we'd like to do is figure out a way to break this logically into smaller and smaller pieces. And so now we have a router, and each one has a switch. So our main router feeds everything, goes to the internet. All 3 switches feed back into that router in some manner. So we still need switches, and this diagram doesn't show that. But so you still have your exterior, your border router, and then interior routers, you have a router for each one of the floors. The other thing that's interesting to note is before we did this, we had a single data pathway. And so that pathway would daisy chain from switch to switch, and that's pretty common to do. If switch B, for example, died, you would lose floor 2 and floor 1. With this model, where we start breaking it down and using more routers, notice that we actually have a couple of pathways that are exhibited in here. And we can actually program the routers so that if router B dies, router C still has traffic, and we can do some workarounds there where we have redundancy. So that's advantage 2B in this, or whatever you want to call it. But we set them up by what we're going to call a subnet. And that subnet says, all right, I have floor A, floor B, floor C, whatever they are. And we haven't talked a lot about that subnet mask yet. And we're going to get closer to it. So remember when we did our examples, it was just 255, 255, 255.0. And we're going to go into some, if I can get my iPad to connect here, hopefully so I can draw on the screen. We want to show you what it looks like. So internally, even though we know IPv4 is running out of external addresses, we still use it internally. It's easy for us to manage. The numbers make sense. We need to look at that subnet mask. So when we did an IP config, you got an IP address and you got a subnet mask. What that subnet mask does is it divides this address, your IP address, into 2 portions. So you can think about it as a sliding pointer and says everything that's all the 1s, that's our network ID. Everything that's all the 0s is our host portion. In other words, a portion that we can change on that network. So if it's a Class C address, Class C addresses are always going to look like that. 255, 255, 255.0, which in binary is this group of 24 ones. So there's 32 bits. So 24 of them are here. The handy thing about a subnet mask, it always is 1s from the left. It doesn't ever go 1, 0, 1. It's always solid 1s and then goes to 0s. So where this ends is where we divide this address up into network ID and host portion. And here's why we pushed you to look at binary before. Because we have to convert to binary to figure out what your the network ID and what the host portion is. So up here, this address, we converted it back to binary. We overlay that mask on it, and it tells us where that pointer is. And so in this case, it's pretty easy. That end piece, 132, comes over here, and the other half goes there. But what if we change that subnet mask? And we'll show you how we do that using something called CIDR. If it's not at those preset locations, our binary math doesn't work. We have to resort to using, our decimal doesn't work. We have to resort to binary. So our 3 default masks for class A, B, and C, so it follows that pattern, 8 ones for A, 16 for B, and 24 for C. So the other way you may see these networks described is a /8, /16, or a /24. And that slash says that's how many ones are in your subnet mask. And that subnet mask, like I said, it divides outside from inside address. And so we're going to work on how to do those. And this is maybe the toughest math piece we have to do. So that's the other way we can describe that network. We can say 192.168.89.127/24. So it says that's how many ones are in there, and we call that CIDR, classless interdomain routing. Well, the beauty of this is we don't have to split just on those blocks of A, B, and C, because those don't always fit our needs. So sometimes we need to change that a little bit. And we need to do something called subnetting. So subnetting allows us to break our network into smaller pieces. So we change where that normally would fall by either robbing bits to the left or robbing bits to the right, whether we need to increase the number of networks or whether we need to change the available size of the network. All right, so this is where it gets a little ugly. So we wanted to divide that network, 192.168.89.0, because we already performed our math on it. We said that's our network. And we want to actually break that into 2 networks. So what we're really doing is breaking it into smaller pieces. And we're saying, all right, I know I have network A and network B. That is a sliding scale. And our book, I think, doesn't necessarily make this as easy to understand as hopefully we can make this for you. So I want to look at this first. So subnet A and subnet B. We've broken it into 2 pieces. So here we've got subnet A, and we've got it both in binary and in decimal, so that you can see what our first host and our last host are. But maybe it makes a little more sense if we start looking at that really in the idea of binary and that sliding scale. So let's come back here a second, because our book goes through it pretty quickly. So we have those A, B, and C networks, and that's our default. So they're either 8, 16, or 24 bits. If I move that just a little bit, I end up with a slightly different value. So this is a chart that actually goes from one side to the other. So if I come back here at 24, that's our default for Class C networks. And what that says is, on a Class C network, I can have up to 200 or 120, where am I at? 255, 255, there it is. 256 subnets, and each host would have 254 clients. So in this lab, that seems to work. I have one IP address, and I have that many clients. I can have 254, because I can't use 0 and I can't use the 255, so I'm really taking 2 off of 256. I have 254 clients. That works in this lab. 32 computers, 33, I got a couple video cameras, some other devices, but I don't have 254 devices in here. And that scale makes sense. What might make sense, though, is I might divide up my network, and I might say, you know what I really need is 2 subnets in there, and I only need 126 in each one. So if I slide that down, I can have more groups, but they're smaller groups. So maybe in here I say, you know, I really need a smaller group, and I need to isolate my desktop computers from the computers up in Lisa Perriot's office. And so then I could have 2 subnets, and I could have each of them separated that way. The other way to go on this chart is I look at that same 255, the /24, and my network's grown. And my network says, oh man, I'm starting to see we have some issues. And so I recently did this with a client. I wanted to divide them up, and for some reasons that were probably a little outside of here, we couldn't divide them quite the way I wanted to. We decided that we were actually going to increase the size of their network. So instead of 254 possible combinations, we're going to raise it up to 510. So again, 512 minus the 0 and the top scale, the 255. So we changed them from a 255 subnet to a 254 subnet. But I have to be able to do the math to know what my IP addresses are, what my network host is, and what range of IP addresses those are. So in here we do a 255, just because that's very convenient for us. But if I look at externally, so if I go to Chrome and I load up our browser, if I can get in there, so I come over here and I put this in here and we look at our router here. So notice our internet address is a /20. So what that /20 says, and we'll go look at the actual numbers, is there are a lot more so if I go all the way up to /20, that means on this network at Peru, I could theoretically have 4,094 devices on that network. And you think, well, man, that's a lot of devices on there. Could I have that many devices at Peru? That's very possible. Because if you look at all of our buildings, so all of our control systems now, security cameras, how many people are on Wi-Fi, all the Wi-Fi access points, everything that's connected to that. Yeah, it's very possible that we could have that. So that's an example of moving up from that base 254 addresses. On your own router at home, most of you are going to have a 254 number of clients. You're going to have a Class C, a default Class C. And in theory, your router could handle 254 clients. Now, does your home router really going to handle 254 very well? No, it's going to choke and do some other things. But conceptually, it could do that. So we use this idea of subnetting. The other way to look at it is classless. In other words, we just say, I want this, or whatever it is I want. So most of the time, what we will say is, I need to buy an internet address from Time Warner Cable, Spectrum, whatever it's called today. And if I actually need to buy one and they have one available, they will say, all right, I'm going to sell you a /30 address. And so they would give you an address. You would actually be able to have 2 hosts on it, which is fine because what you're going to do is transfer it internally, do what's called NAT, and so you have your internal addresses. But your internet service provider then could sell that to 16,000 customers. So they have one IP address on their side, and they can break it into 16,000 networks. All right. So Class C. If we look at Class C, which is really the bottom end of that table, it's very similar. We start out with our top, which we would have /24, but if we break it into smaller pieces, so our internet service provider may have one Class C address. They can actually sell it to 64 people because you only need one address, really. And if you try to buy 64 IP addresses, you're going to be very unpleasantly surprised what the cost of that is now. So we get one Class C address, and we know it's actually, you can put two hosts on there, but using your router and something called NAT, you could put all your IP addresses outside on it, and it would work fine. So this is really the way we divide up our network, or one of the ways we divide up our network. And so there are a ton of questions on the testing for this class. If you do go out and do the TIA Comp test for this, the Network Plus, they test you a lot on this. That's not really the intent of this class, is to pass the test for you. So this is an area where I'm going to say, if you've decided, hey, I want to go take that test, that this is one you're going to have to do some substantial extra studying on, because it's the math on it. You have to be able to work the math and do it on paper in there to be able to pass the exam. Quite frankly, because I don't do it every day, what I'm going to do if I have to break one up is I'll do the math myself, and then I will go out, and there are thousands upon thousands of what we call subnet calculators out there, and I'll plug in my values and say, hey, is this all correct? And so I will get the network ID, the broadcast address, first and last addresses. In other words, what range of addresses I can put on each subnet. And I do it that way. So here, for example, is that same problem. Now, though, we have these subnets assigned. And so our router address, in other words, the base address of this group, here, 192.168.89.1, 89.33, 89.65, and so those aren't intuitive because they're from binary then translated back to decimal. And so this will tell me that base address of where we're at and what we're going from. So it's a little trickier than what it looks like at first. But it's a way that we can break those up using that subnet mask, a tool we have already available. We don't need to do anything else. If I don't run routers all the way through there, those can't talk to each other. The only way each one of those LANs can see each other is through a router. And I have to have that rule in the router that says, hey, floor 3 can actually talk to floor 2. And they have to transfer through a router to be able to do that. What has happened, though, that makes life a little easier for us is there are now layer 3 switches. So I don't have to have a router and a switch. I can actually, in some cases, combine them and use the routing features inside of some of the more expensive layer 3 switches. It sometimes is a cost saving. Sometimes it's kind of equal. Because the better class 3 or layer 3 switches are pretty expensive. They're not, a couple $100. You're going to spend $4,000 or $5,000 for a really decent switch. So which one makes sense in your scenario when you start laying it out? And if you've got multiple stack switches, sometimes it's better to do a router. Just depends on your particular need in there. So here we've taken a network and we actually supplemented it into 8 small networks. So each network has a switch, but it has to connect through that router. So this network, this works, and it gives us 8 small networks. So some businesses that makes a lot of sense for. We break them into very small groups, or we break them into a lot of groups. But there's a problem with this one. that I see right offhand. What have we done in terms of reliability? What happens if that router would fail? We lose all of our networks. We don't have any redundancy. So if that router fails, each network would still, in theory, be able to talk to itself, but it wouldn't be able to get past that. And so we probably need to think about some redundancy scenarios. But how do we send those out? To send out that subnet message saying, hey, you're going to get a subnet mask that's different than that default. And so we send that out with what we call DHCP. So DHCP, dynamic host, says, I have to ask the server for my address, and I receive it back. And so what I can do is map up what computers are in each one of those subnets, and they each get a different subnet mask based on the request. So it can be a very handy, quick way to do things. It's also one of the harder ones to explain. And the math on it is a little tricky. And that's why I said, I'll do the math, and then I will go out on a calculator site. I will not expect you to have to calculate out a subnet mask in this class. If we were doing an advanced course, or we were doing a CERT training course, yes. This course, I want you to kind of understand what it is, so if you run into that, so you have all your network segmented into pieces and it doesn't communicate with another segment, I want you to understand why that's happening and what might be some of the issues. So this idea, subnetting a subnet or variable length subnet mask, is a way we can actually divide things up even smaller. If I have a large enough organization and I try to figure out how I can divide things into smaller and smaller pieces for security, this is one of the ways we can do that. So this says, all right, I know that sales is going to need 120 people, HR 25, and what I'm doing is I am using variable links. So some people get 2 or 5 or 10 computers on that particular link. I will say, having seen this, people do this, implemented this, there are a couple of problems with it. If I look at maximum number of accounts or hosts I can have on there, it minimizes that. I don't get the maximum number of hosts. And if it's not well documented, you're going to drive people crazy when you do this. So this may not be it may work for your situation. Make sure it's well documented. Because if you bring in a new IT company or they come in, somebody else does, or you have a troubleshooting issue, this is a little more complicated, and it's going to take somebody some skill to figure that out. If you have a DHCP problem or a server issue, you can actually see this rear its head. So if you're going to get this complicated, you're going to have some redundancy. You're going to have multiple DHCP servers. You're probably going to have multiple routers involved. But it's a way that we size the group or the size of that network specifically for that group you're in. So when I talk security, I can't have extras. So my WAN link, I'm using up both of those links. I don't have any extra ones, so it gives me a little bit of security from that standpoint. So what it might look like then is this, the subnets, we've broken them up. So again, we said, all right, sales has got a bigger piece, and then certainly the WAN links or the executives or IT, they have smaller and smaller pieces of that. The danger I've seen in this and where it gets ugly is you sized it at this particular point, and you said, man, we're never going to have more than 120 salespeople. And then suddenly we hire, where's that chart? Suddenly you hire 5 more salespeople. And because we made this a little more complicated, sometimes juggling those around and making sure it all fits in our scheme can get a little uglier. So if you've got this, you've probably either got an on-staff IT firm or you're contracting out to one that's doing a lot of service with you. Ultimate security, or one of the better ways for security, yes, but you're always balancing that idea of a trade-off of convenience versus usability and other features, so ease of use. So this works great if you plan ahead and you're accurate on your planning ahead. Unfortunately, that doesn't always work that way. So IPv6 is actually a little easier in a weird way because we have enough addresses. We don't have to use subnet masks. And if you look at the number up there, a single IPv6 subnet is capable of displaying 18 trillion or some huge number. So we're not quite as limited. So we can do a couple of other techniques. Most of our networks internally, though, are not IPv6 at this point, unless you're a really large corporation. But what this lets us do is we can break them down into, we can still use that / nomenclature, and you can break them down into different size organizations by the site prefix. So you can actually break them down very simply. The thing that we do more often now is actually something called VLANs. So yes, we still do subnet. Because our networking technology has improved, we can actually do something called a virtual LAN. So virtual LANs give us the ability to form these groups more flexibly. So in this building, I can have a VLAN or a virtual LAN and segregate my traffic. And I can have it based on geography. So the original VLANs were based on what switch port it's plugged into. And so my switch, that's all I can do. It has to be, I base it on the plug that it's put into. So I could have half this lab on a VLAN for students, half on a VLAN for administration. That would be easy enough to do, even though we're geographically the same. I could put that VLAN over our entire organization, which is what we actually do. And I could have faculty in their offices on one VLAN. Even though we're all over campus, they're in that same virtual LAN. Now, these switches that we've went to now actually see that computer and look at that MAC address. Now, notwithstanding that we could spoof it, but they look at that MAC address and say, oh, I see that MAC address. You're assigned to a particular LAN. So it doesn't matter where I plug in, I can go to the right LAN. The same way on the wireless. I can go, because my computer is recognized and I logged in the right domain, I can actually go to the appropriate LAN no matter where I'm at. So this gives us a lot more flexibility. So here we had our 3 floors, but I can group them a little easier. So now I can say, all right, there's the manufacturing, there's the administration LAN. I do that, so originally, again, I had to group those ports, so it took a little more documentation. So I had to say, all right, this is group A, this is group B, these are plugged into switches. And so my story about one of our IT techs many, many years ago, deciding to clean up an IT closet, and what he did was made a bunch of cables, or bottom, I'm not sure where they came from, and then he started reorganizing it by color, not realizing that those were different LANs on some of the ports. And it took a while to reconfigure this building after he had done that, because people were on the wrong VLAN because they were plugged into the wrong port. So now we have some tools to make that easier. But again, if you don't have it documented what VLANs and how your VLAN structure is, this breaks apart pretty easily. It's a great idea, but again, that documentation is what's going to save your butt. So a lot of times we will have more than that. We will have many VLANs. So we might have a manufacturing VLAN, an administration. We might have a secure wireless VLAN, in other words, for internal use. We might have a guest wireless VLAN. We can apply rules to each one of those groups so that, for example, our guest wireless only has access to port 80 and web traffic, and that's all it can do. It gets shit right out. and it can't see anything inside of our network. So VLANs can be set up to do that. So it allows us to break up our traffic in really small segments. We could put our VoIP traffic or video traffic on a specific VLAN, give that VLAN priority or quality of service, and so that it could send out in smaller pieces. We break it up for security. It's less network equipment, so I don't have to have a separate switch for each group, but I can have them secure on the same switch. I can separate groups for whatever reason I need to, and so I can drive them into little pieces. So most switches now, so your higher end switches, will have and use VLANs. It's not perfect though. And I will say one of the issues I've had that I have seen is VLAN traffic set up from one switch doesn't always pass seamlessly through another. It's supposed to be interoperable, but I have seen some odd things. So be prepared for that. And some of the lower end switches, so you go, oh man, I know we bought all this Cisco equipment, but I just need another 20 ports. I'm going to plug in my TP-Link or something. Be prepared for that not necessarily to work. So the higher end switches, it should be fine. You'll probably see if you plug in a Juniper Networks or a Brocade or whatever switch, you should be fine. But if you plug in that TP-Link or some cheapie, or you get an older switch or there's some issue, you may find that they use slightly different commands, or that they won't pass some of the VLAN traffic, or you can also run into some issues like jumbo frames and some other things. But the VLANs is where we tend to have the biggest headache there. So this is my preferred method to break up a network. To break it into small VLANs, I can control each VLAN separately. I can actually give each VLAN completely different IP addresses inside. So a lot of times what I do is I will set up a Class C network, a Class B, and a Class A, or something weird inside of a network. So like a 10 range, a 172, and a 192 range, and use them for different purposes. And through the router, they can communicate with each other internally. But those VLANs give me that ability to separate the networks up. So I almost always put wireless off somewhere off on its own. And wireless scares me a little bit. So remember, I always approach things with the lens of, holy cow, how can I break into this network? And wireless gives me the easiest entry in a lot of cases, unless I can get into your server closet. So I almost always break off things like wireless, and I put it over there. And I try to isolate items that need low latency. I will put those. So VoIP phone systems off on a VLAN. Then I look at what customers are doing. How do I best break that up to make it as efficient as possible? And so sometimes I make those VLANs bigger than I would have liked, but I also look at the kind of traffic that's going on that VLAN. The reality then is that switch has to process that VLAN traffic, and most of the time a router also has to process that traffic to be able to switch from one VLAN to another. And so if I have users that are all doing, the latest one I ran into that was really high traffic was a document scanning system. That document scanning system sent a tremendous amount of data that they were using. And I actually pulled people back. So they were originally on 2 separate VLANs, and I actually merged them back into one, including the server for that document management system, just because of the latency that it was implying. And then yes, I probably could have upgraded their routers. This was a much cheaper solution than my original, about $25,000 solution I offered to them. So it's great to break things down into the smallest units we can, but be aware there's always a performance hit when we do that. So anytime I have to go through a router, I get some latency, and I get a little bit of lag because it's got to go through that process of doing that. So to do that, we use something called a managed switch. So typically our cheap switches, an unmanaged switch, we plug and play. We don't have to do anything to it. It doesn't have an interface that we can manage. It's about as basic as you can possibly get. A managed switch, or the way the book describes it, it doesn't get an IP address, so we can't even find it. It just sits on our network, passes traffic, doesn't know a whole lot. A managed switch, so this, not my best example using a Netgear, but this might be a managed switch. And so in this case, we assigned port 1 to VLAN 2, ports 2 and 3 to VLAN 10, VLAN 20, and VLAN 30. So we have different ports assigned to different VLANs. It works really well. Again, it takes some modeling to figure out how you're going to do that. So most of our switches that we're going to look at that are more sophisticated, you can interface them with a couple of different ways. There's a web interface almost always. So in other words, if I go to that web address for that switch, I can usually interact with that switch. The more sophisticated way, and to get all of the functions of that switch, tend to be through a command line interface. Cisco has their own command line interface. And if you know that, you can usually work your way around other switches that use command line. They will change it just a little bit, but you'll see that they will be able to be configured very similarly. So only a managed switch can do VLANs. Now, some unmanaged switches do pass VLAN traffic, but you can't tag it at that port. Yeah, that's kind of weird. So you can also do a lot of other things. So a managed switch, oftentimes we have the ability to do things like a lag group. So this is only an 8-port switch, so it's not a great representation, but typically they're 48-port switches. I need to connect them to another switch. In this case, it's actually got a couple of connectors where I can plug in fiber, but if it doesn't have that, I can actually, in some cases, group 3 or 4 of those together into what's called a lag. So in other words, I'm aggregating 3 or 4 connections to the next switch up. So instead of just 1 gig per second, I can essentially transfer 4 gigs per second. Or if I'm on a 10 gig switch, I can do more data than that. So there's a lot of things that our higher capacity switches can do. They don't break in terms of they have a bigger buffer, so buffer overflows are harder to do on them if you're looking at it from a tax system. They tend to have, when you get upscale, they tend to have more robust features. So they will, in most cases, have dual power supplies. Depending on your need, you may or may not have power over Ethernet. So in other words, you can power video cameras and other things like that. You may be able to lock them down. Because I will tell you one of the things with a managed switch, if I'm on your network and your switch isn't locked down, I can do some pretty nasty things. One of them I can do is configure one of those ports. So in this switch, if I looked at this one and I said, oh, look, I see port 5. I'm plugged into port 5, and this switch allows me to mirror all of the traffic for diagnostic purposes over to port 5 for me so I can get a copy of it. Ooh, that sounds a little dangerous because now I've got a copy of all your data on your network. And internally, we're not transmitting most of that encrypted. And so I'm stealing your data pretty easily that way. So just one of the ways we can do that. But that's a managed switch. Actually, those ProSafes are not that bad. That's actually similar to what's in the back of our closet. It would not be my choice except for price, honestly. But then again, price is usually a consideration in those. So typically, this is how we're configured. So we have our network. All of our computers are connected to a switch. And those switches can range from 4, 5, 8, 24, 48 ports. And that's what we actually connect our LAN to. So for example, in this lab, there's 32 computers. To make life more interesting, if you look under the desks, you can actually find them. Each pod only has 6 network connections for some reason. So the architects, when they redesigned our building a couple years ago, we said, hey, we got 32 computers that are arranged in these pods, and they specified 6 network addresses or network connections, and that's what they designed and put in here. So under each pod, one of those network connections runs to an 8-port switch. That 8-port switch then provides the other 3 computers. So there's a little extra jump that I don't like, but it's unfortunate. So that's that idea of a very cheap switch. Those guys were, $25 or somewhere. They were very, very affordable. Not high quality networking equipment at all, but it works for in here. All those computers then and the switches all connect back to our server closet where they're at some Aruba equipment or HP equipment. And there's 48-port switches in there. Due to that idea that now we can map that off our MAC address, these are all on that student network for us that was set up. And I can plug this computer literally in anywhere on the campus, and it'll be on this network here. So if I show you a pathway to get to that server, and you take this computer and you plug it in the administration building or in Gendra, it still should be able to map its way through there because we're assigned to that virtual LAN. The traditional model is this idea of a flat network, layer 2. We have our router, we have our switch, and then our local area network. This VLAN model says, no, you have this. So we have VLAN 1 and VLAN 2. So in other words, we're breaking it up into those virtual models. They don't have to be right next to each other. Now, there is some logic to breaking those into chunks that make logical sense using color-coded wiring and other schemes, but we don't have to. And in fact, I can assume, even in the left block that's got mostly VLAN 1, I could have port 3 be VLAN 17. I don't have to do that in blocks. Some of the older switches we really were a little more limited, so they would do it in blocks of 4 or 8. Almost all of the newer switches we can assign it at any point. And again, the latest technologies are we assign it based on the computer that's plugged into it. Makes life a little easier. So what that does, or how a VLAN works, is we've already talked about everything gets, as it goes through that stack, it gets headers and then finally gets a trailer. It's encapsulated by all this data. So your original data is in the center and it's wrapped around like a burrito rolled up and open up. VLANs just add another tag to that says, hey, this is what I'm looking at and this is where I'm at. When it hits its last leg, so it looks like this, so we add in there a little bitty tag that says, all right, we're shoving in 4 bytes. It says here, and then it takes it back out. So it reaches its destination, it gets stripped out. So for the most part, unless you're getting raw data off a switch, for example, you're not going to see that VLAN tag. You have no way to easily tell on your computer what VLAN you're actually on. So that's where it gets a little trickier from a troubleshooting standpoint is, I don't know what VLAN I'm on unless I can get back to the switch or I'm able to see this traffic raw. So that's where that mirroring the port can reveal that, or if I'm logged into a switch, I can see, oh, you have these. So that documentation is all important. And I know I keep harping on it, but making sure that everything is documented is very important. So I actually have a network I'm breaking up right now into smaller pieces, trying to make it a little more secure. And here's what I've ran into. It's kind of an odd duck. So in this particular network, that VLAN tag gets stolen by the internet service provider. The internet service provider is providing what they call TLS or something, Transparent LAN Service. What it really is they're doing VLANs on their side. And so each one of the locations, so this entity has multiple locations, each entity, all of them are merged together except for the problem of they're using those VLAN tags on their end. I don't have any way to pass VLAN tags, and I can't put that network in my standard function of pulling it into sections. So it's a weird oddity. So in this particular location, to break those up, I'm actually using completely different IP addresses for each group and then blending them together at a router at a central location. It's probably not the best way to do it. I would love to be able to pass VLAN tags, and I'm so used to being able to do that it's kind of got me going, oh, I really need to fix this. But how? The other thing that bothers me a little bit in this case is all of the traffic for this organization passes through the local internet service provider. So not just the internet service traffic coming down, but any intercommunication from one location to another passes through that service provider. And from a security standpoint, it sounds a little sketchy to me. Hopefully it's not, but I would be a little concerned about transmitting anything on there that's very secure. So this week, I went ahead and pulled an assignment. Very few people had done it. In fact, maybe nobody on this one. So the live labs again reared their ugly little head. And I had a live lab that seemed to have some issues, at least when I went back in and tried it again, for getting access. So I pulled the lab 8.1, the switching features. It's interesting. I like it. You can actually find it inside of Cengage if you want to look for it and try it. But you won't see this link anymore, so it's not available when you look at it. So you have your reading, you have a simulation, there is a quiz, and this week if you look at the discussion board, so I had originally left this open for something exciting to come this week, and I decided, you know what, we're week 10, we're on that almost final stretch, let's just give everybody a break on the discussion boards this week. Unless you guys want to object. Oh, wait, Chris, you said? No, okay. No. We will give you guys that discussion board off this week, and just to kind of give you a little refresher. We're going to then, we have essentially 4 weeks left, guys. It's kind of crazy. We're hammering through this as quick as possible. So, one last reminder, if you haven't got enrolled, make sure you do. There are some of the 3-week classes available still that have not closed. Some of them were already apparently closed because they didn't have anybody enroll in them. The one that I would particularly point you in that might be interesting is the Advanced Excel course that Ms. Perriot's offering. It's 2 hours or 2 credit hours in 3 weeks. So it's a great skill builder course. There's some other ones. There's a couple of courses available in different subjects, so you might look at them if they fit your schedule. I will warn you that you're limited to taking one and that they are going to be a little intensive because it's the same amount of time as what you'd spend in a 16-week course compressed into 3 weeks. So great way to get some credit, but you'll be working your butt off a little bit for it. So, and I have not taken a 3-week, but I've done some 5-week courses at UNO, and they will push you a little bit in that short a time frame. So be prepared for that. But if you know up front and you have the time, it's a great thing. All right, if you haven't enrolled for spring, those schedules are up, and you will have a hold until you contact your advisor or stop at the One Stop Center. You can certainly also do that. I know we're not always available every hour of the day when you guys need us, so we've set up that One Stop Center, especially if you're here on campus. That's kind of handy. Make sure you get enrolled. The quicker you get enrolled, the quicker you're assured that the courses you need are going to be offered. Because I think in the spring, they're probably going to be a little draconian on which courses they're cutting by enrollment pretty quickly, is my understanding. So, all right, any questions? No? All right. See you guys all here on Wednesday.